Is this one or the other one? So I am Pablo Barcellona. I am in a group of Stefan, and I did this work with Hassan and Akbar. I want to thank you, the organizer, for inviting me, and you all, everybody, for being here. So basically, I will try to explain you the dispersion interaction between chiral molecules, which are mediated by chiral surface. The chiral surface are really important because they can enhance the interaction, these chiral interactions. Usually these chiral interactions are really weak in free space. So this chiral media, which basically enhance the interaction via many body interactions, can be really important. So I will try to, first of all, explain the interaction between the chiral molecules and the light, as explained by quantum electrodynamics. Okay, so basically, first of all, the dispersion interaction are interaction between molecules, polarizable molecules, which arise because of fluctuating dipoles, because of the Heisenberg principle. This fluctuating, so the change inside the atoms, they can't be controlled with absolute precision. They fluctuate, and these fluctuating dipoles are responsible for the interaction, this dispersion interaction. But there is also another point of view. So basically, the quantum vacuum. So the quantum vacuum is a really active place. Continuously, virtual photons are created and destroyed by vacuum fluctuations, and the molecule can exchange this type of excitation of the electromagnetic field. So basically I will focus on this kind of explanation in order to get the van der Waals interaction between these chiral molecules. And the coupling is described, can be described, for example, by the multipolar coupling. So basically this interaction Hamiltonian can explain the building blocks for explaining the interaction of the molecules with light are this process of the emission and absorption of one virtual photon. I wanted to, in particular, to study interaction between chiral molecules and light. The more simple object which is chiral are the human hands. So basically, each hand is the mirror image of the other hand. And basically, you cannot superpose the hands together. This is really similar to chiral molecules, so they don't have any plane or mirror image. And so basically, you cannot superpose this type of molecules with each other. They have really distinctive properties. They can, for example, rotate the plane of polarization of light by a certain angle, or they can absorb with, in different degrees, left and right circular polarized light. This phenomenon related to the rotatory strength, which is defined in terms of these electric dipole matrix elements and magnetic moment matrix elements, and so basically these are basically the elements of the electric dipoles between two states and energy states. And under reflection, they have really simple properties. So basically, the electric dipole moment is change sign. The magnetic dipole moment is an axial vector, and the rotatory strength is a pseudoscalar. So the rotatory strength for one molecule has a certain sign, which can be positive or negative, but for its enantiomer has the opposite sign. And many processes are really sensitive to this so they are discriminatory with respect to different enantiomers. The discriminatory effects play an important role for separate enantiomers. For example, a really recent procedure is the Coulomb effusion imaging, in which you shine a laser to a molecule, a chiral molecule, you induce a ionization, and the fragments, they fly away because of the Coulomb repulsion. And basically, so if you look at the momentum distribution of these fragments, you can achieve important information about the chiral information of these molecules. There are also other techniques, for example, rotational spectroscopy with circular polarized light, or liquid chromatography. But I wanted to stress that there is another method could be another method to separate enantiomers, so basically dispersion interaction, which are discriminatory. For example, the single molecule Casimir-Polder force, so the force between a molecule and a surface, is discriminatory. And I wanted to show you basically that the van der Waals interaction, they are also discriminatory. So they are different, so they change, so some components of this van der Waals interaction, they change sign if you consider the enantiomer of one chiral molecule. So first of all, we can, in order to describe the interaction of this molecule with the light, we start with electric molecules with this multipolar coupling, and we do a unitary transformation in order to get this effect in Hamiltonian, which is well known in literature, which contains the is quadratic in the field and contains the polarizability of the molecule. The van der Waals interaction is obtained by using second-order perturbation theory. So the atoms A and B, they are represented by vertical lines, the photons by red wavy lines, and the time go upwards. So if you want to read a particular time in this diagram, you have to take an horizontal line. Now we wanted to generalize this consideration to a chiral molecule. In this case, we introduce a dual pair of fields, electric and magnetic fields. So basically, we introduce the magnetic multipolar coupling, which is also important for chiral molecules. These pairs of electromagnetic fields, this label for the electric, this one for the magnetic, and the ground state polarizability, which depends on these two upper script, lambda, lambda prime. So the components in which lambda is equal to lambda prime, they are basically the electric and magnetic polarizability. The off-diagonal elements are the chiral polarizability, which depends on one electric and one magnetic dipole moment. And they are really important for chiral molecules. The lamp shift can be obtained with zero-order perturbation theory, so just taking the expectation value of the interaction Hamiltonian over the ground state. But this is not interesting for us, so we will consider the van der Waals interaction, which is obtained, as I told you before, by second-order perturbation theory. Because in this case, the Hamiltonian is quadratic in the field, so quadratic in the annihilation and creation operators. This is the application basically of the second-order perturbation theory. The intermediate states are two photon states. And if we evaluate this energy, we get this final expression, which contains two polarizability and the classical green tensor. In particular, I have introduced the upper script for the green tensor, which are defined by these formulas. So they just are application of an Abel operator over the green tensor. So this is one. So in this previous expression, I sum over all possible electric and magnetic labels, and each component, this U, lambda 1, lambda 2, lambda 3, lambda 4, contains two polarizability, which gives the order of magnitude of the interaction. So the order of magnitude of each component depends on the number of electric and magnetic dipole moments in this component. the inclusion of a general environment is taken into account via the green tensor, so we are considering interaction between molecules with a magneto-electric body which can possess also chiral properties. And a more interesting thing is that under reflection, these off-diagonal elements, which are basically the chiral polarizabilities, they change sign under reflection. So there are components. If we consider one molecule and it's an enantiomer, this component, they change sign, so they are discriminatory with respect to different enantiomers. This is the well-known electric contribution, and this is the chiral electric contribution, which contains one chiral polarizability and one electric polarizability. As I told you before, the diagonal elements, this one and this one, are the electric and magnetic polarizabilities, and the off-diagonal elements are the chiral polarizabilities. An important symmetry of this type of interaction is the duality transformation, duality invariance. So if we exchange electric and magnetic properties, we should obtain the same interaction because we are summing over magnetic and electric labels. In fact, this is not surprising because, Maxwell equation without any free charge and without any free current, they are also duality invariant, so I expect that dispersion interaction between neutral particles, they are also duality invariant. In this case, each component transforms to each other in a pairwise fashion by doing a duality transformation, so doing this type of transformation on the polarizability on the green tensor. For example, here I will show you an example. There is this chiral electric contribution. If we do a duality transformation, we can obtain directly the chiral magnetic contribution. As I told you before, so basically the chiral contribution, they are discriminatory, but they are in generally too weak with respect to the dominant contribution, which is the purely electric contribution. For example, if we consider the free space case, we see that the order of magnitude of the electric dipole moment is this one, where H0 is the Bohr radius. This one is the magnetic dipole moments are the order of magnitude of the Bohr magneton. So basically, m over c divided by d is the defined structure constant. If we consider that, so we have the leading term, which is the purely electric contribution, which contains two electric polarizability. Then we should have the chiral electric contribution, but because of symmetry consideration, it can be shown that this contribution is vanishing. And this can be explained by the Curie dissymmetry principle, because if you have a chiral molecule, in order to distinguish the entityness of the molecule, you should have another chiral molecule or a chiral plate to distinguish the entityness of the molecule. So this is why this contribution is 0. So the next or the leading term is the chiral contribution, which reads, which is this expression for isotopic molecules, and it's well known in literature. But the problem is that this chiral contribution compared to the pure electric contribution is roughly 4 orders of magnitude smaller. So it is, yeah, it's discriminatory, but it is really a small contribution in the total force. So that's why we are interested in the inclusion of the chiral media in this type of interactions. In this case, the interaction can be explained in terms of two-photon exchange, as I told you before, but the difference when we introduce a media is that the photons can be reflected by the chiral media. In this case, the green tensor is the sum of the bulk green tensor, so the free space green tensor, and another part which is the scattering green tensor, which takes into account the reflection of the electromagnetic field in the surface. How can we realize the chiral media? They has been realized, for example, let's see, so basically they are metamaterials with unit cells. So for example, this one is a unit cell which are repeated in all the directions. and they are multi-layer system. So in order to have high chirality or high high optical rotation, superadiquism, all these effects, we should have a lack of a symmetry plane above, parallel to the substrate. So they can be realized with several unit cells, for example this crosswire, this gold helix, or wood pile structure. We will anyway consider an idealized case, so the interaction between the molecules, chiral molecules, and a perfect chiral plate, which rotates, which reflects a p-polarized wave to an s-polarized wave, and the other way around. So basically it's changed the polarization of the light by p divided by 2, or minus p divided by 2, when looking at the direction of the wave vector. In this case, we find, so basically before we have seen that the chiral electric contribution was vanishing, but with the introduction of this chiral plate, we have a non-vanishing chiral electric contribution, which is in the so-called non-retarded limit. This R is the separation vector between the two molecules. So let's consider an example. So the interaction between this electric rubidium atom and the chiral molecule meti, cyclopentanone. And yeah, they always have these strange names. And we fix the position of the chiral molecule, so the molecule A, and we see the force acting on the molecule B, which is in general not parallel to the separation vector because of the presence of this additional surface. In order to quantify the degree of attractiveness, we see this parameter, which is the scalar product between R, the separation vector, and the force. And we see for both components, for the chiral electric and for the electric, and we compare this parameter for both components. So what we see basically is that the chiral contribution is maximum in this point and this point. So when they are parallel to the surface, but they have a large distance along the y direction. In this case, the chiral contribution is 1 order of magnitude smaller than the pure electric contribution. In this case, so when we are here, so when the molecules they have the same y direction, they have the same y position, and they have a large distance along the z direction, we have a chiral contribution which is repulsive and 1 order of magnitude smaller than the pure electric contribution. So the chiral contribution, so we have achieved something better, so the chiral contribution can enhance or reduce the total interaction, but is 1 order of magnitude smaller than the total interaction. We can do something more. So for example, in this case, we have 3 molecules. One chiral molecule A and the chiral molecule C, which is the enantiomer of this molecule A. And we are interested in the force acting on the middle molecule B. In this case, because the electric and magnetic interaction are not discriminatory because of the high symmetry, the force acting in the middle molecule is vanishing. So only the chiral contribution, which is discriminatory, is acting on the middle molecule. This interaction is enantiomer selective because the molecule B will be attracted or repulsed from A depending on the chirality, so the impedance of this chiral molecule A. So in this case we have found some interesting result in which the chiral contribution is the dominant one. The van der Waals so we have studied, in conclusion, the interaction between these chiral molecules and the light by using quantum electrodynamics. The chiral contribution can be repulsive with respect to electric contribution, which are always attractive. And we have seen that the impact of general environments could be really important to achieve enhancement of the chiral contribution. So the chiral media can enhance or reduce the interaction because of many body interactions, as explained also by Andrea Gambassi and Akbar Salam. So these many body effects can play important roles in this type of interactions. And we have seen also a configuration where the chiral contribution is the only contribution possible. So what could be interesting is how to achieve the separation of enantiomers by using van der Waals interactions, so interaction between the chiral molecules. I would like to thank you, everybody.
So the talk is open to questions. Stefan, please.
Two questions. One about the metamaterials that you're trying to use in order to increase the chiral interactions with the plate. In order to make a metamaterial that has chiral response, you need to increase, as you rightly said right in the beginning, both the electric and the magnetic interaction. So in order to increase the chiral interaction with the plate, you also increase the electric interaction with the plate. Do you gain anything?
Yeah, so also the electric. So the electric, and basically the electric control, if you include the chiral plate, it does not influence the pure electric contribution because...
I mean in a realistic metamaterial where you try to artificially enhance the chiral contribution. You also always enhance the electric contribution.
It has also electric properties, so I expect also there should be some electric properties also in this type of materials, yes. This is in fact idealized materials which I don't know if could be realized experimentally.
The second short question is coming back to the last slide. This one, yeah.
This one?
So, yes, this one. So you said if molecule B is right in the middle between A and C, then you have this directed force, right? So this discriminative force.
Yeah, which is twice.
Yeah, sure. But that of course means that molecule B has to be exactly in the middle between A and C. How exactly?
So this is a really good approximation. I mean that we consider like the molecule B as point-like. So this is a really good approximation. In fact, we didn't investigate if the molecule B is so it has a certain size, and we shift the position of this molecule. We didn't, because there is also this paper of Butcher about this chiral molecule near the chiral plate, and it shows basically that by changing the position of the molecule, you have basically destroyed this effect. In fact, this is, I think, a nice picture, and I don't know if it can be realized experimentally.
Did you check? So you have quite a large difference between the dipole interaction and the chiral interaction, of course, in amplitude. So did you check if you have a higher order, meaning third, fourth order, any interaction between the dipole and the chiral one, which is maybe giving larger terms then in terms of amplitude, or didn't you go to any?
You mean when you have various molecules, for example? So
if you have higher order graphs, because I think with your formalism, it's
you mean, for example, quadrupole.
Yeah, exactly.
Quadrupole. So basically, this contribution, I think they are important when you have large molecules. So when you have large molecules, these quadrupole elements, this quadrupole contribution can overcome also the electric dipole contribution. So they're not overcome, but give important correction to the pure electric contribution. So the approximation here is basically that the molecules can be considered small ensemble of particles, really small, and I think this should not play any role, this type of quadrupole contributions.
You don't expect any new effects?
I expect that, new effects if you consider larger molecules. So competitive contribution with also respect to the pure electric contribution.
Omer, please.
So I'm also interested in the question of how to realize the defective chiral plates. And the metamaterial idea sounds like a great one, but I'm a little concerned that the weird electromagnetic properties that you get with metamaterials, like defective chirality, tend to be associated with resonance effects, because the wavelengths are associated with the feature size and the patterning. So I'm wondering if the transition frequencies that are relevant for Casimir-Polder forces went too high for metamaterials to work. I'm not sure. But I'm also wondering, the condensed matter physics community is all excited about topological insulators. And is it possible that you get interesting van der Waals effects with chiral molecules above topological insulators?
So basically, if I get to the question, so basically this type of material, they are really strong to implement because these metamaterials, they are, they have high chirality for certain frequency, but not for all the range of frequencies. That's the problem. So they wanted to investigate so this type of metamaterials, which holds for all frequencies and not just for a certain range of frequencies. And the second question was about
Topological insulators.
this non-reciprocal media. In this case, I should expect a new interesting result in non-reciprocal material because you cannot use the transpose property of the quintensor. Here we use this transpose property of the quintensor which related the quintensor in transpose. We expect that all these force should be different for this type of non-chiral materials, or to this type of non-reciprocal media, but I didn't investigate that.
Yes, please.
Just coming back to René's question, just to comment on that. So yes, you could take into account electric dipole polarizable molecule and an electric quadrupole polarizable molecule. Interestingly, there is a chiral contribution between two mixed electric dipole quadrupole polarizable molecules, but that vanishes on isotropic averaging. So it holds for the fixed molecule case.
But the amplitudes, are they comparable to the first order?
So the mixed dipole quadrupole would be of the same order as the mixed electric dipole magnetic dipole.
Is there any way to measure that?
Let's talk about the manipulation. The coffee is going to become cold now. Let's make the last question.
So typically when people want to discriminate chiral molecules on surfaces, they actually absorb at chemical distances or van der Waals distances, so 3 angstrom or so. And when you do that, in addition to handedness, you get footedness. Because you have a different geometry, right, it distorts the chirality and you get an additional source of chirality actually. Yeah. And that's what discriminates typically the chirality on surfaces. Did you include that?
No, I didn't include that.
Okay, let's thank the speaker one more time. Let's